We're going to take a look at how the resting membrane potential is established in this video. The resting membrane potential is the membrane potential when the neuron is at rest, and that means it's just sitting there, it's not receiving or sending any nerve signals at all. And the resting membrane potential for a lot of neurons is minus 70 millivolts. And there are some differences in some neurons, but a lot of them will be right around minus 70 millivolts. So make sure that you know that. So that would be a good number to memorize. So make sure you memorize that the resting membrane potential is minus 70 millivolts. And the reason that it's minus 70 millivolts is because there's more negative charges inside the cell than there are outside the cell. So we've got a nice picture from your book over here, just showing the inside of the cell. You've got more anions, which remember are negatively charged ions inside the cell, than you do outside the cell. But when we go to draw the membrane potential, remember that we're just going to draw what's going on inside the cell, because otherwise we get too confused. So if I want to draw the resting membrane potential of minus 70 millivolts, I'm just going to draw those negative charges inside the cell, and that's it. And I'm just going to draw 7 of them, and that's just how I do it. And it just gives me a relative way to show how big it is, because if I'm drawing, another membrane potential in another cell of maybe minus 40 millivolts, it just allows me to show the difference in the membrane potential. All right, this is really important to know. So the resting membrane potential is due to 3 things. So we've got the concentration gradients of potassium and sodium ions. And we've got the membrane permeability to potassium and sodium ions. And this is due to potassium leak channels and sodium leak channels. And remember that the leak channels, these ion channels, don't have any gates on them, and they're just open all the time. Okay, so the potassium or the sodium can go, travel through those all the time. There's no gate on them. And then we also have the sodium-potassium pump that will also be contributing a little bit to the resting membrane potential being a negative number. And then it also helps maintain the resting membrane potential at minus 70 millivolts, because it actually keeps the potassium and sodium concentration gradients. So this is why potassium is going to be higher inside the cell than outside, and sodium is going to be the opposite, and it's going to be higher outside the cell than inside. All right, so just a reminder. So remember that the equilibrium potential for potassium was minus 94 millivolts. And remember, when potassium is at equilibrium, that means that the electrical and chemical driving forces are the same size but going opposite directions. And so when you add those two together, the electrochemical driving force would be 0, and potassium would not move one net direction or the other. And then remember that the equilibrium potential for sodium ions is plus 60 millivolts. And again, it's the same thing. When sodium is at the equilibrium potential, the electrical and chemical driving forces are the same size and going the opposite direction. So when you add those two together, again, the electrochemical driving force would be 0, and sodium would not move one net direction or the other. Okay, so just a little reminder there. All right, so let's draw out how the membrane potential gets to a resting membrane potential of minus 70 millivolts. All right, so we're going to start with our cell here, and we're going to put our membrane potential to start at 0. So that just means that there's an equal amount of plus and minus charges inside the cell as there is outside the cell. So we're not going to draw any pluses or minuses inside the cell because they're going to be equal to what's outside the cell. Okay, so we're not going to draw anything there. And then we also have drawn our sodium and potassium concentration gradients. So we've got a lot more sodium outside the cell than inside, and potassium is just the opposite. So potassium is higher inside the cell than outside. So you do need to memorize that. That's really, really important to memorize the concentration gradients for sodium and potassium, knowing which one is higher where, if it's inside or outside the cell. Okay, and how we got those concentration gradients was because of the sodium-potassium pump. So remember, the sodium-potassium pump is going to be pumping 3 sodium ions out of the cell and 2 potassium ions into the cell. And remember, that's primary active transport because we're moving the potassium against its gradient. It's going from low to high concentration. You've got a lot higher concentration inside the cell, so it's going up the gradient. And then also the sodium is going up the gradient because it's moving from lower concentration inside the cell to much higher concentration outside the cell. So it's also going up the gradient. So both molecules are going up their gradients. And we're also going to have to be directly using some energy. We'll have to use some ATP here, so that's primary active transport there. Okay, so we've got our concentration gradients, and we're going to put in a leak channel for sodium and a leak channel for potassium. All right, so these leak channels are very specific in their shape. And the sodium leak channel is only going to let sodium through, and the potassium leak channel will only let potassium ions through. Okay, and let's say that there's an equal number of sodium leak channels and potassium leak channels right now. Okay, and we're going to kind of ignore the sodium potassium pump right now as well, so we'll kind of come back to that. All right, so with the leak channels, sodium is going to want to move down its concentration gradient, going from high to low concentration. So sodium wants to move into the cell. And then potassium wants to move the opposite way because it wants to go down its concentration gradient, going from high to low concentration. So our chemical driving force for sodium is going in, and the chemical driving force for potassium is going out. And we don't have to worry about any electrical driving forces because there's no membrane potential where it's 0. Okay, there's no charges we have to worry about inside the cell. And as soon as the sodium comes in, potassium leaves. And so if you have one positive coming in, one positive charge leaving, everything balances out. So our membrane potential stays at 0. Okay, but this is not what's happening in our neurons. So the number of sodium and potassium leak channels is not the same. So in our neurons, the membrane is actually 25 times more permeable to potassium than it is to sodium. So we've got 25 times more potassium leak channels than we do sodium leak channels. Okay, so we're going to have a lot more potassium leaking out of the cell than we have sodium leaking in. So what's going to happen to our membrane potential if we have a little bit of sodium coming in, but we've got 25 times more potassium leaving the cell? So our charges are not balancing anymore, are they? Okay, we've got a lot more positive charges leaving with our potassiums than coming in with the sodium. And so we're going to start to end up getting negative charges inside of our cells. Okay, because there are some proteins in here that are inside the cell, because there's lots of proteins inside cells, and the proteins have negative charges on them, and they can't leave the cell, so they're in there. And as all those positive potassiums leave, well, those negative charges start to show up because those positives aren't there anymore to cancel them out. So our membrane potential is no longer 0. And we end up eventually getting to minus 70 millivolts, our resting membrane potential. Okay. And if we take a look at what's going on now, so our sodium, now we have to look at our electrical driving force, because now we've got a charge. So our concentration gradient stays the same, chemical driving force is the same. And if we take a look at our electrical driving force for sodium, well, sodium says, hey, opposite charges attract, I want to come in. So electrical goes in, and if we add these two together, our electrical chemical force for sodium, sodium really wants to go in the cell. Okay, because both the chemical and electrical forces are going in. Okay, but there's not a lot of leak channels for sodium to come in. So sodium really wants to come in, but there's not a lot of opportunity for it to get in. Okay, now what about potassium? Well, concentration gradient, we're still going out, so chemical driving force still going out, but what about our electrical driving force? Well, electrical driving force, potassium with the positive charge, it sees those negative charges inside the cell and it says, hey, electrical driving force wants to go in. Well, if we add our electrical and chemical forces together, they're the opposite direction. So who's going to win here? Well, we've got to take a look at our equilibrium potential for potassium. And if you remember, that's at minus 94 millivolts. So that's when your chemical and electrical driving forces are the same. Okay, so at minus 94 millivolts here, these two are the same. Now, if you're at minus 70 millivolts, is this, so we're going to make our chemical driving force the same size as what it was at the minus 94 millivolts, because that hasn't changed our concentration gradient. But what about our electrical driving force? Does potassium want to go in as much at minus 70 millivolts as it did over here at the minus 94 millivolts? Because there's actually more negatives inside the cell at minus 94 millivolts, isn't there? Okay, and then at minus 70 millivolts, there's 1, 2, 3, 4. Whoops, I got one too many. So there's only 7 negative charges in here at minus 70 millivolts, and there's 9 negative charges at minus 94 millivolts. So at minus 94 millivolts, potassium wants to go in a lot more because there's more negative charges. But at minus 70 millivolts, it still wants to go in, but it's like, not as much. So our electrical driving force isn't as big. We're going to draw a thinner line than what we had at equilibrium at minus 94 millivolts. So when we add the electrical and chemical driving forces together for potassium, the chemical driving force wins. And so our electrochemical driving force for potassium, it wants to go out, but it's not as big as what it is for sodium, is it? Okay, sodium really wants to get in that cell. And potassium's like, yeah, I want to leave the cell, but you know, I'll leave eventually. Okay, it's not as in a hurry to leave the cell as what sodium is to get in. Okay, and it's just because that electrical force is going the opposite way of the chemical force. Okay, but potassium has a lot more opportunity to leave the cell because there's 25 times more leak channels. Okay, so one thing to kind of burn into your brain, which would be really good to remember as we're going over our neurons, is that sodium always wants to go in. And then potassium always wants to go out of the cell. Okay, so if you just remember that, that'll help you a lot. So sodium always wants to move into the cell and potassium always wants to leave the cell. Okay. All right. Okay, and then the other thing that contributes a small amount to the minus 70 millivolt number is this sodium potassium pump. Okay, notice we have 3 positive charges on the sodiums being pumped out and only 2 positive charges being pumped back in. So we're 1 different positive charge here. So we've got 1 more positive charge being pumped out than being pumped in. So that contributes a little bit to the negative 70 as well. Okay, most of it's coming from being 25 times more permeable to the potassium with the 25 times more potassium leak channels, but a little bit comes from the sodium potassium pump as well. Okay. All right, so that's really, really important to understand, okay, how we got to this minus 70 millivolts. All right, so just to kind of reinforce all this, very important to remember that in our neurons, we have 25 times more potassium leak channels than we do sodium leak channels. So it's going to be a lot more potassium leaking out of our neuron than sodium leaking in. And when that happens, if we have a lot more potassium leaving the cell than sodium coming in, that's going to leave us with a negative charge inside the cell. Okay, so the membrane potential will become negative. Because you have all those positive charges leaving, not enough coming in, and so those negative proteins have no positive charges to cancel them out. Okay, and then these are just pictures of what we drew on that other cell. And this is just showing that we've got the sodium leak channel down here on the bottom. And then here we've got 25 times more potassium leak channels up here on the top. And so we've got a lot more potassium leaving the cell than sodium coming in. And so the inside of the cell is going to become more negative. Okay. And then eventually we end up with a negative membrane potential of minus 70 millivolts, and that'll be our resting membrane potential in most of our neurons. Okay, and then we talked about our sodium-potassium pump here. The sodium-potassium pump is actually really important. That's going to maintain our concentration gradients, because when the sodium leaks in, we need to make sure that we pump it back out, right? To keep the sodium high outside. And then when the potassium is leaking out, we need to pump it back in to keep the potassium concentration high inside the cell. So the sodium-potassium pump is really important to make sure that we keep the sodium high outside the cell and potassium high inside the cell. So sodium-potassium pump, very important, maintaining those concentration gradients, and it's also going to maintain the resting membrane potential. So sodium-potassium pump, very important. Okay, and then just showing the sodium-potassium pump, we've got the outside of the cell up here on the top, and just showing you the 3 sodium being pumped out. This red thing is the ATP, and then we've got 2 potassium being pumped into the cell. And you can also see the concentration gradient for sodium and potassium there as well. Okay, and then just reminder, we talked about how the sodium-potassium pump also contributes a little bit to the minus 70 millivolts of the resting membrane potential. It doesn't contribute a lot to the minus 70 number, but a little bit, just because you've got 3 positive charges you're pumping out and only 2 positive charges you're pumping in. So it does contribute a little bit to the negative charge inside the cell. Okay, a couple of important questions here. So these might make some good test questions. So we've got the equilibrium potential for sodium, and then the equilibrium potential for potassium. And then here's our resting membrane potential of minus 70 millivolts. So our first question, the resting membrane potential is much closer to the potassium equilibrium potential. So why is that? So why is our resting membrane potential a lot closer to where potassium will be at equilibrium than to where sodium would be at equilibrium? So hopefully you were thinking about how the membrane is a lot more permeable to potassium. Remember, there's 25 times more potassium leak channels. So potassium has a greater chance of getting closer to its equilibrium than sodium ever will. So the reason why is because the membrane is more permeable to potassium. So I would know that for the next exam. That would be a good test question. Okay, and then our second question that I would know for the exam. So why don't we just, with our resting membrane potential, why don't we go all the way to potassium's equilibrium potential? Why don't we just go all the way to minus 94 millivolts? Why do we stop at minus 70 millivolts? Okay, so the answer to that is because we do have some sodium leaking into the cell. And if you have some sodium coming in to the cell, bringing its positive charge, that's going to make it more positive. And so it's not going to get as negative all the way down to minus 94 millivolts. So because there's So because we have sodium leaking into the cell and making the membrane potential more positive. So that's why we don't go all the way down to minus 94 millivolts. So that would be good to know for the exam too. Okay, and then this is just a summary of the neuron at the resting membrane potential of minus 70 millivolts. So for sodium, there's a very large electrochemical force. Sodium really wants to get into the cell, but there's not a lot of sodium leak channels for sodium to get in. And then for potassium, the electrochemical force for potassium wanting to leave the cell is smaller than the electrochemical force for what sodium has. But potassium does have a higher permeability because there's a lot more potassium leak channels. And then we also have the sodium-potassium pump, which is really important to maintain the sodium and potassium gradients and maintain the resting membrane potential of minus 70 millivolts.